Okay, let's begin the lectures given by the award winners. The first lecture is given by Professor David Gross, who is clearly one of the most distinguished scientists in modern times. He was part of the major builders of Standard Model, the most distinguished theory in mankind. Explains everything in the universe, hopefully. And anyway, he will continue. And his title is Quantum Field Theory, Past, Present, and Future.
Can you hear me? Okay. Well, it's really wonderful to be here. The last few days and yesterday was spectacular, and I wish I could be here for the rest of the Congress, but I have a very important meeting in Chicago which begins today on Monday, and I have to get back to Chicago by Monday, so I have to not follow my usual custom and talk too long, or rather I need to talk too short, so I'm going to begin right now. And I'm titled my talk, Quantum Field Theory, Past, Present, and Future. And roughly speaking, what I'm going to try to briefly run through is a history of the development of quantum field theory from the beginning, from the origin of quantum mechanics 100 years ago. This year we celebrate the birth of quantum mechanics. And then the development over the 20th century, which led to the standard theory of particle physics, among the rest. And then I will turn to the present, where we're attempting to unify all the atomic and subatomic forces of nature together with quantum gravity, which has led us to string theory as a possible solution, which has, in the last decades, led us to think about the quantum mechanics of space and time, quantizing general relativity, and more thinking about what space-time is made of, how space-time emerges, perhaps from some more fundamental description. And I'll make a few remarks about beyond quantum mechanics or QFT. So we are indeed celebrating 100 years of the development of quantum mechanics, which began early in the century. And although Planck's great discovery was based on light, and trying to understand the spectrum of black body radiation, which is, of course, relativistic particle theory in principle. Light, after all, is relativistic. Most of the early work on quantum mechanics was completely non-relativistic, and the idea that light itself could be a quantum phenomena was foreign even to Planck. Einstein, of course, understood that given Planck's discoveries, light had to have properties, some properties of a particle, and he sort of invented the quantum nature of light, the photon. But the big advance happened, non-relativistic description of atoms, with Rutherford's discovery of the nucleus and the structure of atoms. And the Bohr model, which was some kind of arbitrary, now we understand semi-classical treatment of hydrogen, was so successful in explaining the periodic table and calculating the Rydberg constant that it set the stage for the emergence of quantum mechanics as we know it. And all of this was non-relativistic. De Broglie suggested that matter, not just light, behaved as waves. Einstein said waves can behave as particles. Du Bois said that particles can behave as waves. And Stern and Gerlach discovered spin, in effect. All the ingredients were there for the emergence of quantum mechanics 100 years ago. And of course, the great advance happened in exactly 100 years ago in 1925 with Heisenberg's invention of matrix mechanics, the existence of non-commuting observables, very strange to classical physicists. And then in the following year, Schrodinger's approach, a wave equation for some kind of wave, and Dirac's understanding of how one could quantize any classical system by replacing Poisson brackets with commutators. And to some extent, by 1927, well, this was refined by Born, Jordan, Heisenberg, and Bohr to understand that quantum mechanics was really a probabilistic theory in which you could calculate probabilities for events. And Pauli put forward the uncertainty principle, the exclusion principle, which essentially was the theoretical discovery of fermions. And all of this was completed in a very short time. So often happens in physics, ideas, experiments build up, and then there's a phase transition to a totally new way of thinking about the universe. 1927, the story was more or less complete. This is the famous Solvay conference of 1927, where all the inventors of quantum mechanics came together, argued, but more or less agreed on the structure of quantum mechanics as we essentially know it today. So we have Planck, Einstein, Bohr, Heisenberg, Dirac, Schrödinger, they're all there in color. The stage was set for relativistic quantum mechanics, of course. These pioneers realized that quantum relativity was essential. One had to make relativistic quantum mechanics. And that was achieved very shortly afterwards by Paul Dirac, who was trying to make relativistic Schrödinger's equation for the electron and avoid negative energy solutions. Instead, he discovered the square root of the Poisson equation, if you want, which introduced his famous gamma matrices, and he thought would eliminate negative energy solutions. But it was soon realized that the Dirac's equation, which explained the hydrogen atom even better than Bohr, led inevitably to the existence of negative energy states, or with modern interpretation, antiparticles. For every particle with any quantum numbers that must exist in a relativistic quantum mechanic theory, particles with the opposite quantum numbers. He predicted, in effect, the positron, which was discovered only a few years later. That made relativistic quantum mechanics not a one-body problem. You could not write down a theory of an electron in a potential, say the Coulomb potential. Inevitably, once you have relativity and quantum mechanics, there are antiparticles which inevitably are produced, and relativistic quantum mechanics is inevitably a many-body dynamics. But we did possess a classical theory, Maxwell's theory of electrodynamics, which was so dominant in the 19th century, And it was straightforward, following the principles, the new principles of quantum mechanics, to quantize the electromagnetic field. The field became the operator, was now an operator, not a classical observable, and Maxwell's Hamiltonian theory or Lagrangian theory could be quantized directly. And immediately, these young inventors, Heisenberg, Dirac, Pauli, Weisskopf, Jordan, and others, turned to quantize electrodynamics. But there were problems. The problems were really not conceptual, but technical. We're dealing now with a gauge theory, with redundant degrees of freedom. How do you deal with those? There were ultraviolet divergences. Immediately when you started calculating, nobody could deal with those. So although the basic equations and approach to QED, quantum electrodynamics, were set forward by 1932, it still took over 2 decades to truly understand quantum electrodynamics. Fermi, however, immediately tried to apply construct what we would today call an effective field theory, a field theory that could describe the weak, what we call today, the weak interaction that's responsible for beta decay. Very successful, effective field theory, we would say at the time. And Yukawa suggested that perhaps the strong nuclear force could be mediated by a heavy photon. He suggested what we call today the pion, the carrier of the nuclear force that between protons and neutrons, which were the only known elementary particles aside from the electron at that time. But he thought the pion would have spin 1 because all carriers of force have spin 1. The only one that was known was the photon. Of course, it turned out to be a pseudoscalar, and its discovery gave a great boost to the idea that you might describe the nuclear force a la Yukawa, or the weak nuclear force a la Fermi by quantum field theory. Quantum electrodynamics came to its final form after World War II, when experiments began to see deviations from simple Dirac theory of the electron. Quantum fluctuations would change the charge, the magnetic moment of the electron, and experimenters measured these very small effects, stimulating theorists, Feynman, Schwinger, Tomonaga, and Dirac, to finally understand how to do meaningful calculations in quantum electrodynamics. Understanding that what we measure, and therefore must take into account in our equations, and the solutions must account for, are not the parameters that one puts into the theory that describe the mass and the charge at arbitrarily short distances, but what we actually measure, which is always at some finite distance. This is the program of renormalization, which, although they didn't truly understand, allowed them to do calculations without encountering infinities, and to start calculating using a marvelous graphical and conceptual technique that Feynman discovered, Feynman diagrams, and that enables one, as you know, to calculate with incredible precision the quantum corrections to the naive predictions of QED. And as fundamental physicists, we are incredibly proud of tests of our fundamental principles, like the anomalous magnetic moment of the electron, or today of the muon, and other examples of precise calculations where we can measure the anomalous magnetic moment of the electron to 1 part in a trillion, as well as calculate those corrections to the same degree of accuracy. A monumental achievement which has taken many decades, but there is no other place in physics where such incredible accuracy is even pursued, much less achieved. It's really characteristic of fundamental physics that we continue to try to test our theories to better and better accuracy. Because we all know that the only judge of the truth of our theories and our understanding is nature. So we continually ask nature, are we right? Are we right? So far, in QED, for example, nature says, so far you're right, do a better experiment. At the same time, with the success of quantum electrodynamics, people tried very hard to extend quantum field theory to the other, much less understood forces in nature, those that act within the nucleus, the weak nuclear force responsible for radioactivity, and the strong nuclear force that holds nucleons together. And many new techniques were developed at that time. Already in the case of quantum electrodynamics, Feynman came up with a reformulation of quantum mechanics, which has motivated us ever since, given us a whole new perspective on quantum mechanics and all of its forms, and provided the basis for many new ways of calculating, where the amplitude for particles to propagate from point x1 to x2 in time t is, where the amplitude is written as a sum over all possible paths, weighted by a phase, the exponential of I times the action, the classical action of the system under discussion, which probability is the square of that amplitude, and that gives us a whole new way of thinking about quantum mechanics at the conceptual level, as well as the understanding of how semi-classical or the classical world emerges when Planck's constant is small or the action is big as the dominant saddle point in these integrals, these path integrals. Those path integrals, path integrals have been generalized, of course, to any quantum system, including quantum field theory, where one is now not just integrating over paths, but over fields, and an infinite dimensional integral, which our mathematical friends throw up their hands and say, what are you talking about? What the hell is this measure? What does this mean? We still don't really know in most interesting cases. And the true understanding of what integrals like this mean in a rigorous mathematical sense, in some ways, many of us regard as the most important question that our mathematical friends could answer. It's one of the Clay Millennium Prizes and probably the hardest for a theory, which I will certainly come to. So over the years of the 60s, 50s, people tried to develop tools for dealing especially with a strong nuclear force. There was no classical theory to quantize, and there was no obvious theory. In the spirit of physics, some people decided to concentrate not on the dynamics, but on the observables, to try to construct a theory based on the observables. The observables we have for relativistic quantum mechanics are largely restricted to S-matrix elements. The unitary many-body particle Hilbert space of operator that describes the amplitude for two particles which are collided, say at CERN, boom, and produce many outgoing particles. The amplitudes for those processes, which is what our experimental friends measure, are the basic observables. And already early on, in the 40s, 50s, Wheeler and Heisenberg said one should focus on these and not try to invent a classical theory and quantize. This, of course, is what our experimental colleagues at, it's a picture of course, the accelerator at CERN, the kind of modern detectors. Conceptually, all of these are just fancy modern successors to Rutherford's famous experiment in which he figured out the structure of the atom. These, of course, use bigger, more energetic collisions and much fancier detectors, but they discovered the Higgs eventually. So in the 50s and 1960s, there were many important theoretical developments in our understanding of quantum field theory, the quantum theory of fields. One important development was the connection between quantum field theory and statistical mechanics, which is kind of based on the simple idea that if you consider quantum field theory not in a background space-time, a Lorentzian background space-time, but in a Euclidean background space-time, where time is imaginary and periodic. So if you want a cylinder in time, then the time evolution operator, as t is replaced by I beta, and beta is periodic, looks like replacing the time evolution operator with a Boltzmann weight. And a integral over paths in Lorentzian space, when continued in this way, on a periodic imaginary time, looks like the same as calculating the partition function of a system at fixed temperature. So there's an analytic continuation, if you want, between quantum field theory in d, spatial and one time direction, and thermodynamics in d spatial dimensions. This is incredibly rich correspondence that has greatly informed both thermodynamics, system mechanics, and quantum field theory, and led to an incredibly useful over many years between people who do, say, high energy particle physics and condensed matter physicists who are interested in the thermodynamic properties of macroscopic quantum systems. The renormalization group was invented towards the end of the 60s as a tool to understand quantum field theory as well as phase transitions with remarkable success. Conformal field theory, which describes often the nature of quantum systems at values of parameters or temperature, which undergo a continuous phase transition, was developed and with great success by Wilson and others, and has had enormous impact on relativistic quantum mechanics as well. One of the important developments, in retrospect, of course, is the generalization of Maxwell's theory and an abelian gauge theory of electrodynamics to non-abelian gauge theories, which Yang and Mills did already in 1954. This generalization was immediately tried by many people to apply to be applied to this quantum field theory of the quantum version of this non-abelian gauge theory to just understand the ill-understood, totally ill-understood nuclear forces. But the problems were immediate. They were known, for example, to Pauli, who supposedly had done this mathematical generalization on his own and realized that it implied that the photons, the charge carriers, the carriers of the non-abelian charge of such a quantized theory would be massless, like the photon. And since there were no other massless spin 1 particles ever observed, such theories had no application. So he never published his results. But when Yang gave a talk at the Institute describing this work, Pauli would barely let him talk. All other attempts to apply these ideas to particle physics, to fundamental forces in the beginning, in the 50s, early 60s, failed. Because in the case of the weak interactions, where it was by then natural to understand that these forces were sort of vector-like, chirally vector-like, the symmetry is clearly broken, and it was evident to many, including Pauli, I think, that it is simply inconsistent to gauge a broken symmetry in the obvious way. This was solved in the early 60s by Higgs and Broughton Anglaire and others. The mechanism of breaking the symmetry, a phenomenon which is pervasive throughout all of physics, almost all symmetries, beyond the space-time symmetries that were emphasized by Einstein and others, are broken symmetries, and magnetism, for example. But in the case of a gauge theory, the broken symmetries, the spontaneous symmetry breaking, in other words, the discovery that the system has a vacuum, a stable vacuum, which is asymmetric, like in this kind of potential, break the symmetry and give the gauge bosons a mass. And therefore, they're not excluded by experiment. They simply might be too heavy ever to be observed. This, of course, was the basis of the gauge theory, the SU2 cross U1 gauge theory of electromagnetism and the weak interactions of Weinberg, Glashow, and Salam, and others, which turns out to be correct and is an essential part of the standard model, which has now been verified by the discovery of the Higgs to some extent. Strong interaction was much harder. There was no understanding of the strong interaction. There were many new particles being discovered all the time. It was not clear which was elementary, what was the theory. There was no classical theory. The coupling, the interaction was very strong, so there were no methods to calculate, even if one had a theory. Couldn't use perturbation theory. And famously, the discovery that really broke the ground, which I unfortunately can't describe in detail, was an experimental discovery at SLAC of using electrons to probe the structure of protons, much as Rutherford used alpha particles to probe the structure of atoms, and discovered that it looked like protons were made out of point-like particles that looked like they were not interacting at all at very short distances over very short times. That was really astounding, and certainly had a big influence on me. I'd been working on ways to test the nature of the proton by using these deep inelastic scattering experiments, and the results convinced me that proton was made out of quarks. The various sum rules that we derived that indicated the protons indeed, that the constituent, the charged constituents of the proton looked in all senses like quarks. And yet quarks, we've never seen a quark, so what if they were interacting weakly, how come you couldn't pull them out of the nucleus? And of course the answer turned out to be, again, non-abelian gauge theories, where the sources of the gauge fields are 3 instead of 1, electromagnetism, 2 in the case of weak interaction. Now we have 3 colors and anti-colors. And such a force, as it remarkably turned out, although it would be Coulomb-like in classical gauge theory, in the presence of the quantum vacuum, populated not just by electron-positron pairs, but also by quarks, which are charged and affect this paramagnetic, as it turns out, medium, actually force the flux, the field lines of the chromodynamic field to be squeezed as much as possible into a flux tube. And such a flux tube behaves very much like a string, constant tension, which means the force between a colored quark and an anti-quark never decreases, and that not only explained, remarkably, the fact that the quarks interact very weakly at short distances, but also that they can't be pulled apart at large distances. That led immediately to the theory, quantum chromodynamics. This is actually what it looks like if you solve the equations using lattice gauge theory, and you have heavy quarks, pull them apart. You see the flux is contained in this tube, and in fact, in terms of a potential, the potential does not saturate. It's a linear potential which confines the quarks. This theory is now, 50 years later, been tested literally thousands of times with accuracy exceeding 1% in every possible. This is my favorite picture of the decrease of the strong interaction, coupling, the strength of the interaction as a function of distance. So this is large distance, this is short distance. This is actually not the most up-to-date picture, but it's the same. It's now well tested in literally hundreds of experiments to a level of about 1% or less. It's also an amazing theory. I like to boast about it. I call it a perfect theory, at least by the standards of the past. Most theories have infinity somewhere. Electrodynamics, if you go to very short distances, everything blows up. And actually, we believe that electrodynamics, and hopefully our mathematical friends will prove it, they have for simpler theories of this type, that such a theory is inconsistent. The only sensible theory of quantum electrodynamics, a U1 gauge theory with one charged particle, is a theory where the charge is 0, where there's no coupling. Note in QCD. QCD, the bare coupling, the coupling at short distances is 0. And it grows, but it saturates at some point. The quarks pull themselves together. There's no longer any force. So, no problem. Also, because the force gets weaker at higher energies or shorter distances, this is a theory, unlike any other theory we've ever had, which has no place where it breaks down. You go to higher energy, shorter distances, theory becomes trivial. By itself, it would be totally complete. It also, in a sense, has no adjustable parameters, and that's really remarkable. The goal of physics is to come up with a theory or a set of ideas where everything is fixed. And that, to some extent, is true in QCD, except for those quark masses. Quarks have masses, and QCD says nothing about those. Those have to be measured and put into the theory, but they play a very small role. At least the light quarks are so light you can almost neglect their mass. And then everything is calculable. All dimensional parameters, like the ratio of all masses, can be calculated. Now, of course, there are other aspects of the theory that we don't understand, the quark masses and the mixing, and why are there 3 colors and not 27? And then, of course, there are other forces in nature, like gravity especially. But these features of the theory are truly novel and amazing. How can you calculate in such a theory with very strong forces? Well, the only tool we have at the moment for precise, controllable first principles calculation is lattice gauge theory, where one replaces those infinite dimensional integrals by finite, large dimensional integrals, and take the limit as the lattice spacing goes to 0. And that has reached a new level of maturity using both the fact that computers are getting better and better every year, and theorists are getting smarter and smarter every year. And over the last 40 years, these calculations have achieved an incredible ability to calculate the static properties like the masses and, for example, of strongly interacting particles, which now can be calculated to incredible accuracy, better than 1%. The mass of the proton, the mass of the neutron, and the mass difference, the small mass difference of the proton and the neutron, and every particle that has been discovered. That, however, good lesson for us, has taken 40 years. And it's required 2 things. It's required an improvement in the power of computing power by a factor of 1 billion. That's Moore's law acting over 40 years. But it also required an improvement of 1 billion in theoretical ingenuity, algorithms, finite size effects, chiral symmetry breaking. Together, that's a factor of 10 to the 18, and that was required. So these gauge theories of the strong and the weak, and of course the electromagnetic interaction, constitute, together with the experimental discovery of all these particles, the quarks, in 3 families, and their lepton friends, the electron and neutrinos, together in what I would prefer to call the standard theory, describing the 3 forces of nature, the 3 gauge groups, the 3 charges, the 1, 2, and 3 charges, and the masses of these elementary constituents determined by the Higgs mechanism. Higgs mechanism doesn't determine the mass of the proton. That's the energy of the confined quarks and gluons. And without the Higgs, you'd still have the proton and its mass. But it does describe the mass of the elementary leptons and quarks, these fermions. And it seems to work, it could work, from the highest possible energy that we can conceive of without gravity, the Planck length, to the size of the universe. We know of no limitation. There's much about this standard theory model that is not explained by the standard model so far, but mostly having to do with the Higgs sector, the masses of the quarks and their mixings. This is a remarkably already unified picture. It's all gauge theories, 1 charge, 2 charges, 3 charges. They fit, everything fits together beautifully. And so naturally, we have been trying to unify. But just the existence of this standard theory has had enormous implications for other areas of physics, especially the early universe. So at the same time the standard model is being completed, astronomers, with the discovery of the CMB radiation, were beginning to attempt to understand the history of the universe. And although it's hard directly to see the very early universe, theoretically we can, because we have this theory, which gets simpler and simpler as you go to higher and higher energies, temperatures, density in the early universe. And so interesting things happen. We predict and study and look for experimental signatures, for example, the various phase transitions. In the case of quantum chromodynamics, between nuclei, confined quarks, but as you heat them up, these nuclei, we predict, melt into unconfined quarks and gluons. That can be explored on Earth, and we try to study the phase diagram of quark-gluon matter, for example, at ALICE, at CERN, at Brookhaven, and it's absolutely fascinating, but I don't have time. So what have we learned, very conceptually, big picture from the standard model? Well, we've learned that matter is made out of charged spin 1/2 fermions, quarks and leptons. We've learned that the forces are described by quantum gauge field theories. And they come in 3 phases. 3 kinds, 3 phases. Maxwell's theory, 1 charge, has in the Coulomb phase, the force is long range, 1/r², everything you learned in high school. The electroweak theory, SU2 gauge theory, 2 charges, flavor, up, down, charm, strain, exists in another phase because of the Higgs mechanism. It's screened. The force is screened. The gauge bosons W and Z are massive. And this Higgs mechanism is generated by what so far looks like a elementary scalar field theory, but somewhat unnatural. And one of the main experimental and theoretical goals of the next decades is to truly understand in a fundamental way whether this simple picture is correct and why and how. And finally, the strong interactions, 3 charges, color, which exist in a confined phase, where the forces are confined, you cannot separate the quarks or the gluons. That's the standard model. Beyond the standard model, well, it's pretty complete, amazingly successful. But there are many indications from experiment and theory that there's much physics not understood beyond the standard model. Neutrinos have mass. That's easy to correct, but we don't even know whether the neutrino is its own antiparticle, a scandal, actually, of current high-energy physics that we haven't answered that question over all these decades. Baryon, a lot of baryons in the world, very few antibaryons. We can understand how that can happen, but we're not sure exactly how. The universe, astronomers tell us, mostly consists of dark matter, as far as the matter content. Astronomers see it through its gravitational effects and map out its distribution in the galaxy and in the universe, but we've never observed it on Earth directly or produced it in accelerators. That is the biggest experimental challenge we face. I would have been absolutely sure that this would have been discovered 10 years ago. It's really surprising that we haven't yet understood the nature of dark matter, but we will. It's out there. We can see it. We can measure it. So we will learn what it is. Then there's dark energy or cosmic acceleration, which is a different kind of problem associated with gravity, but there's many open questions about the cosmological constant that might explain it. Is it constant, really? Is it decaying, etc.? What is the fate of the universe? From a theoretical point of view, we're driven towards unifying these forces that are so similar and particles that fit together so neatly. The nature of the Higgs mechanism is still bizarre and ill understood. The whole system of flavor masses and masses of these quarks, which can differ by 9 orders of magnitude, we have no idea where that comes from. Why are there 3 families, generations? And then, of course, now with the connection with astrophysics and cosmology, there are many important theoretical questions that require gravitational and particle physics input. So they're going to be answered, of course, the usual way by both experiment and theory. Theory, is easy to imagine all sorts of solutions. Experiment today is much harder. But there are plans, beautiful plans, being put forward throughout the world to go one step beyond our current exploration by an order of magnitude at least. One of the leading contenders, of course, is CERN's plans for the future beyond the LHC of constructing a 100-kilometer tunnel that could be used for both E+, E- collisions and eventually in the future for proton collisions. There's a similar proposal here in China, CEPC, which intends to build a large tunnel and do E+, E- experiments, which are critical at the moment to explore this Higgs sector. And then eventually such a tunnel could be used to collide protons. That's a very exciting development, which I have been slightly involved with over the last 20 years, led by Yifeng Wang here. And I fervently hope for the good of China, for the good of science, for the good of the world, that this project is approved. It's an incredibly realistic and wonderful project in its late stages. All it needs is approval. If anyone's listening, please approve. So, from a theorist point of view, the question that one of the most important questions is, how do the forces unify? Right after the Standard Model was developed, you could extrapolate the theory. Strong force got weaker, the electromagnetic force got stronger. Just using simple theory gets simpler and simpler as you go to higher energies, so extrapolation becomes simpler. And it was discovered that the forces kind of come together at a very high energy, very close to where gravity becomes a strong quantum force. The so-called Planck length that Planck understood over 100 years ago when he realized he had to introduce a fundamental unit of action. And together with the velocity of light and Newton's constant, you have all the dimensional parameters you need to characterize all physical observables. The weird thing, of course, is the Planck length is so small, 10 to the minus 33 centimeters, energies are so high, there's no way we can directly probe such distances or energies. But theorists can. And if gravity is becoming essential, we must start treating gravity quantum mechanically. And attempts to do that, by the way, and attempts were tried immediately after the development of quantum mechanics. And I understand that one of the reasons Einstein was so opposed to quantum mechanics was that nobody ever came up with a quantum theory quantum theory of his theory of gravity. And all attempts failed because gravity is the dynamics of the space-time metric, of space-time itself. And the quantum fluctuations of space and time, when they become very strong, sort of space looks like this, or space-time, and everything breaks down. Uncontrollable fluctuations, which kind of informs us that we have to go beyond Einstein's theory. And luckily, we had string theory. String theory naturally turns out to be able to unify gauge forces that underlie the standard model and gravity in a totally natural way. In fact, one can't avoid gravity if one, in string theory. In fact, string theory came from particle theory, from the attempt to understand the forces between quarks, understand the phenomena of strong interactions. Now we understand that a meson, for example, has this flux tube, looks like a fat string, but string-like behavior was deduced from observation of scattering amplitudes of protons and neutrons around towards the end of the 80s, and that's how string theory emerged. So in string theory, these flux tubes are really strings with quarks attached at the end. And more we understand in a deep way that gauge theories and string theories are different ways often of looking at exactly the same physical phenomena. In string theory, these open strings, flux tubes, mesons, you can close the strings. In fact, you have to close the strings for mathematical consistency. And once you do that, you get a sector with no charges at the end, a neutral sector, a universal sector, which turns out to be gravity. Can't avoid it. You want to describe mesons, you have to describe gravity. When people were trying to describe mesons in this way, that was regarded as a problem. It then became a virtue and a possibility of unification. Are, in some sense, all particles different vibrations of a superstring? It definitely could be. In fact, it's really the only comprehensive, well-formulated, well-based attempt so far at such a unification. Now, in recent years, this kind of duality between different ways of describing the same physics has exploded. Not just open and closed strings, but quantum field theory in Minkowski space, in our approximate space-time, and strings in a background space-time which has a well-defined boundary, like anti-de Sitter space, turn out to be remarkably the same theory, different dual descriptions of the same theory. This gives us, for the first time, in a very limited sense, a way of actually defining string theory non-perturbatively. It's simply quantum gauge theory in Minkowski space. So this has totally dominated string theory and fundamental theory and quantum gravity for the last 30 years. Enormously powerful tool. It's resolved one of the mysteries of quantum gravity that was realized by Hawking in his study of black holes. If you drop quantum systems, any system, into a black hole, you seem to lose information. You can't see what happens in the black hole. But he discovered that black holes radiate and disappear eventually. What happens to the information? That has driven enormous theoretical work by relativists and quantum field theorists and string theorists for the last almost 50 years, and has recently been resolved in many ways by string theory. Is information lost? Well, these black hole paradoxes can be formulated in these cases where we have this exact, we believe, exact, physicists say exact. It would take 400 years for this to be rigorously proved mathematically. Say ADS-CFT between a well-understood, quote unquote, quantum field theory cousin of QCD, supersymmetric cousin of QCD in just in 4 dimensions, and quantum string theory in ADS space times a sphere. So Hawking claimed that black hole formation evaporation violates quantum mechanics, but we can set up a system which is a quantum mechanical system with no space, no gravity, or reduced space, but no fluctuating gravity, a fixed space-time, and quantum gravity in a bigger space-time. For example, a black hole in ADS5 is dual to a quark-gluon fireball in this SUN supersymmetric quantum field theory in Minkowski space. These theories we understand, the gauge theories, and they are definitely unitary theories which do not lose information. They're dual to black holes. This encouraged Hawking to give up. He agreed. No information lost. But today, with much more work, beautiful work in the last few years especially, we understand in much more detail how the information is not lost. Much more work remains to be done. This and many other indications are that space-time is emergent. This duality is between theories in totally different space-times. Much of space is kind of emergent in those dual descriptions. That means gravity, of course, is dynamical space-time. We have many, many examples now where some or all of space emerges, can be thought of as emergent. And this duality, this kind of emergent is really novel and fascinating, and one of the main subjects of current present research. Geometry, in some sense, is dual to the entanglement structure of the quantum dual state, which is non-gravitational. We don't really have any good example of the emergence of time. That's really conceptually hard to imagine. And then, where time is crucial, is the history of the universe. The universe, when we are trying to solve a theory which contains gravity, especially quantum gravity, we're trying to construct a theory of the universe, the whole space-time manifold. The universe is the history of space-time, the history of space, if you want. And that includes understanding the beginning and the boundary, if there is a boundary, and the end. And we simply have never had to encounter such a problem in physics before. What determines the initial conditions? That's something physics has never addressed. But if you're trying to solve a unified theory of gravity and all the other forces, that's what you need to do. And we don't even know whether physics is capable of it. We don't have any example of that. There are proposals, Hartle-Hawking universe, et cetera, things like that. But in our current theories, everything breaks down at the beginning. So we don't know really what we're doing. If space-time were to be emergent, if we could understand the beginning of the universe, say, or more generally, is quantum mechanics ever going to be modified? This has been tried forever. And the answer is, of course. To some extent, as physicists, we know from our history that every concept we have will be modified. That's at least been true until now. I'm sure it will be true in the future, but how? Every attempt of quantum mechanics for the last 100 years that has been tried is not consistent with experiment and or logic. But If space-time is emergent, quantum mechanics at the very least will look very different. What we mean by physics will look very different. Typically, what we mean by physics is we set up some experiment, initial condition, we make predictions about observations in the future. But if time, in some sense, is emergent, as it more and more appears to be, I have no doubt that quantum mechanics, in some sense, will look and be very different. Rings, brains, all consist in quantum field theories and quantum gravity. They all are related, connected. But the total framework, we don't know. Quantum field theory, until recently, was sort of the framework that gave rise to the Standard Model. String theory at first seemed to be different, but now we know they're really the same in some dual fashion. Quantum field theory is a framework. It's not a theory. You don't test quantum field theory. You test the Standard Model. And there are many standard theories, different quark masses, whatever. There are many theories in this framework. String theory originally seemed to be special. It had no dynamical parameters. It might be unique in some sense. But even though all the parameters in our perturbative semi-classical construction of string theories, there are millions, in fact, an infinite number of string theory vacua in these solutions. So, no parameters you have to put into the theory, but an infinite number or enormous number of possible vacua, just as bad. So I like to think about theory space, the space of all theories in a given framework. What are special in quantum field theories, which we barely understand, are conformal field theories. I'm not going to describe what they are, but they are special points which are under incredibly more precise mathematical control. If mathematicians want to actually prove the existence of quantum field theories in a rigorous way, obviously CFTs are where to begin. They can be perturbed. Conformal field theories have no scale. The world has many scales, but these theories can be perturbed, and for large distances, you can control those perturbations. You can try to perturb them by so-called irrelevant operators, which become important at short distances. Those are much less well understood. There are a finite number of relevant perturbations, an infinite number of irrelevant perturbations, and they usually end up in meaningless theories. Some irrelevant perturbations are much more interesting. String theory could be thought of as an irrelevant perturbation of quantum field theory. But I suspect that this theory space that we know about today is perhaps just a small part of the space of all possible consistent quantum theories. We simply don't know. We don't know whether string theory is just a lucky example of a UV complete theory or not. So in a fundamental sense, the future of quantum field theory is unknown. We don't know where it sits in the space of all theories. And the final goal, of course, would be a unified framework that consists of all consistent, at all scales, quantum theories, relativistic quantum theories, and even better, a unified theory. What particular theory of that framework is the real natural world? Particle physics, this is the problem of unification of all standard model of gravity. Uniqueness, what picks the particular standard model out of this big framework? Oops. And it's telling me I have to go, which is true. But I'm almost at the end. What picks the theory? The other big problem conceptually is cosmology, as I indicated. How did the universe begin? Now, I believe these are connected. String theory has 10 to the 500 vacua, but none of them look like the real world in the sense that any of them which breaks enough of the symmetry to look like the real world at the beginning makes no sense. None of them, all of them encounter complete breakdown at the Big Bang. It could be that in a more unified way, what picks the unique theory, like the standard model, from the framework, like quantum field theory, is the fact that these theories must have a consistent description of space and time from the beginning to the end. So they're connected. And obviously connected with the nature of space and time, which is probably necessary to understand to begin to answer these questions. So there we are. These are difficult problems. Now mostly, these fundamental problems are mostly explored theoretically. And there I always remind myself of Einstein's encouragement and warning: the successful attempt to derive delicate laws of nature along a purely mental path, which is what theorists often do, by following a belief in the formal unity of the structure of reality, all fits together and makes sense, encourages continuation in this speculative direction, the dangers of which everyone vividly must keep in mind who dares to follow it. So I'm optimistic. I truly believe that once a fundamental question becomes a well-formulated scientific question, like the beginning of the universe, which has only become well-formulated, addressable by experiment, observation, and mathematical model recently, it will be answered in your lifetime. Probably not mine, but many of you. So keep going. Thank you.
Okay. Well, thank you very much, David. I think you have given a spectacular lecture about the deep achievement of modern physics leading to the understanding of nature. And we hope we can continue in the future. Thank you for the spectacular lecture. Okay.